And we will start with geometry-based approaches. Geometry-based approaches to trajectory mining. And there is a pioneering work by Laube et al. That proposed basically 5 patterns, basic patterns on location, direction, and movement which can be mined from trajectory data. Yeah, and of course, as always, with some basic proposals, there are several extensions to these patterns over time. But those 5 basic patterns are really some kind of the core work here, or the pioneering work here in geometry-based trajectory mining. So what are the patterns? The first one is called convergence. Here it says that at least m entities pass through the same circular region of radius r regardless of time. So most of the patterns are somehow defined in terms of a kind of density. So you need some minimum number of objects passing through regions, and the regions are typically determined or defined by some radius. Yeah. So in that case, convergence says those trajectories pass through a given region of a given radius regardless of time. So they can be there at completely different time slots, but the most important point is they pass through the same region of a given radius. That is convergence. Recurrence is that at least m entities visit a circular region of radius r at least k times. So they appear recurrently. So they move, or they visit the particular region k times. So it's the same pattern like convergence, but now it reoccurs k times actually. So reoccurrence is convergence that reoccur k times. Yeah? So we have a third parameter here for this reoccurrence definition. Yeah, and then there are 3 more. So encounter, first of all, left up here, is at least m entities are inside the same circular region of a radius r, assuming that they move with the same speed and direction. Yeah, and that can be, for example, a traffic jam at some point, at some moment. If cars still keep moving in the same direction, but they have more or less the same speed and more or less the same direction. Yeah, so that is an encounter, or defined as an encounter. Then we have the so-called leadership pattern, where at least m entities are within the circular region of r, like always before, but now they move in the same direction, and at least one of the entities, which is the leader, is heading in that direction for at least t time steps. Yeah, so even more specific than encounter. So it's a kind of encounter, but one of those guys here which which participate in the encounter is the leader, saying that he or she or it is there for at least t time steps. That need not to be the case here. Yeah, so an encounter may, for example, evolve to a leadership, for example. Yeah, and an intuitive example is, for example, bird migration. Yeah, and then we have the 5th thing, which is called flock patterns. Flock pattern, at least m entities are moving within the same region of r again, and move in the same direction during a given time interval. So in that case, we have again probably a traffic jam, which happens through a given time interval. So different to encounter now is that we have this particular time constraint, that it has to be not only an encounter, which may happen at just one time slot, but flock pattern is a kind of encounter which happens over a given time interval, which needs to be parameterized by this S here. Yeah, so they are all patterns about locations, movements, direction of movements, possibly also speed, because time sometimes plays a role, sometimes not plays a role. Yeah? And as I said before, those are the 5 basic trajectory patterns defined by Laube et al. And there are a lot of extensions, but very often a lot of approaches try to somehow map their problem on those patterns, and then try to come up with good solutions to compute those patterns. Yeah. Yeah, and then there are some extensions or alternative patterns. So all these patterns are typically based on the idea of high frequency patterns and a kind of density-based notion. So we saw that in the basic patterns already by Laube, a minimum number of trajectories have to come together in a region of a specific volume. Yeah, as I said before, beside of those patterns, basic patterns, other frequent patterns have been proposed to be interesting. For example, frequently followed paths or frequent sequential patterns. Yeah? So if there is a path of trajectories, or if some or a minimum number of patterns trajectories follow the same path, or at least a similar path, like this blue one here. So this is the prototype path of all those trajectories following the same prototype path somehow. Yeah? So that could be, for example, an extension to the basic patterns of Laube et al. Yeah? And as I said before, most of them are based on the concept of frequent patterns. So very often the specific algorithms, the specific methods are variants of a priori or FP growth style frequent pattern mining approaches. Yeah, here are some examples. For example, computing frequent sequential patterns. So this is a work from 2005, which proposed to transform each trajectory in a line with several segments. Yeah, and for that purpose, we need a distance tolerance measure, and all trajectories or trajectory points inside this distance tolerance are summarized into one segment. Yeah? So here you see, for example, this distance tolerance here is epsilon, and as long as, and here is, between this point in time and this point in time, you can draw this line here, and as long as the actual trajectory doesn't leave this this tolerance band here, so to say, of distance epsilon, stays this in this bandwidth here, the whole trajectory is somehow summarized by this one segment here between this point and this point here. Yeah? So this is just in order to somehow get rid of a very, very detailed representation of the trajectories, because as you see here, you just want to have some kind of prototyping segment pattern, yeah, segment path, and the first step here is this transformation of trajectories into more coarse segments. Yeah? And then similar segments are grouped. The similarity, of course, you need similarity in order to group them. So you use clustering typically. So similarity is based on the angle and the spatial length of the segment. Yeah. And finally, the grouping is based on a given distance threshold. So each group is represented by a region around the medium segment. Okay, that's easy to do. And then frequent sequences of regions are just computed with respect to some minimum support threshold, like you know that from frequent pattern mining from KDD1. Yeah? So you can apply some variant of a priori or stuff like that. Yeah, so another interesting work from 2005, maybe frequent mobile group patterns. So a group pattern is a set of trajectories that are close to each other within a distance less than a given threshold, yeah, and for a minimum amount of time, also constrained by some threshold. So min dist is the distance threshold, and min time is the time threshold. In that case, direction is not considered. There are extensions that consider also directions, but here's just the basic work. And also, again, here they use their a priori algorithm to compute the frequent groups here. Yeah? That's basically the basic idea. And there, as I said before, are several extensions to that, considering directions and stuff like that.